My dear students, in this chapter Chemical Kinetics, we have a very important topic, that is collision theory. So in which we generally study about the energy and orientation factors. So before starting this topic, let us watch a video so that the concept of collision theory becomes clear to you. See the video.
Collision theory on bond formation and reaction rates. The collision theory explains why chemical reactions occur and the rate at which they occur. The reaction time of a chemical reaction is how fast the chemical reaction occurs. When we talk about collisions, we refer to particles crashing into one another to break bonds. Bonds form between atoms that are held together by opposite charges. How does this affect a chemical reaction? The theory states that some collisions are effective and some are ineffective. Just because particles in a reaction collide does not necessarily mean that they will react. Particles must collide with sufficient kinetic energy to form a successful product. In order to break existing bonds to create new bonds for the product, the reaction must have enough activation energy. Activation energy is the required energy needed for a reaction to occur. For example, in order for a large rock to roll down a hill, the person must first put in enough energy to get the rock over the bump. A chain reaction occurs once the product begins to form. If the concentration and/or the temperature is great enough, it will increase the speed of the particles, which is directly related to the increase in collisions. This results in a faster reaction rate by decreasing the activation energy.
Dear students, in continuing with the chapter Chemical Kinetics, we'll be discussing a very important theory, that is the collision theory. Now, this theory was given by two scientists, Max Trott and William Lewis, in the year 1916 to 1918. And this theory is somewhat based on the kinetic theory of gases. And a very important aspect of this theory is that reacting species, they collide with each other to form products. Now, reacting species can be atoms, they can be ions, okay, and they can be molecules. So it's the collision of these reacting species that is responsible for the product formation. Okay, so few very important underlying aspects are there in this theory which we'll be discussing. First of all, you must have a clear understanding of what collision frequency is. Now, collision frequency is the number of collisions that take place per second per unit volume of the reaction mixture. That is, what all collisions are taking place per second and per unit volume of the reaction mixture. It's basically called as the collision frequency, which is shown by, or which is represented by, the symbol Z. Fine. Now, you know that in a particular reaction, the collision frequency is very high. If you go to the collision frequency, it can be 10 to the power of 25 to 10 to the power of 28. Now, this is a very high collision frequency. Okay. But if we look at the product formation, it is, we can say, not at par with this collision frequency. So, the product formation is quite slow. It's slow than what it's showing. So it means that there is some few, we can say, underlying aspects which are responsible for the lesser number of the product formation. Okay. So in product formation, it is the effective collisions which count. That is, though the collision frequency can be of a very high magnitude, but the effective collisions, they decide the product formation. Now, what are effective collision? The collisions which actually produce products and result in chemical reactions. Okay. So, though the collision frequency can be of very high order, but the product formation is very less. So that basically tells us about the understanding of the effective collision. That is, those collisions which actually are responsible for the product formation. Now, when we discuss this, or when we study the aspect of this effective collision, we come to know that there are two barriers which are basically hindering the formation of the product to a very large extent, and these are the energy barrier and the orientation barrier. Okay, so we'll be discussing these two barriers, energy barrier as well as the orientation barrier. Now, when we talk of energy barrier, so molecules must possess minimum amount of energy which is called as the threshold energy. Okay, threshold energy. So this is the energy barrier. That is, only those molecules will result in the product formation, or only those reacting species will result in product formation which have got this minimum amount of energy, which is called as the threshold energy. Fine. Secondly, it is the orientation barrier. Now, like suppose there are two molecules or there are two reacting species which are colliding with each other, but the orientation of these two species is not in line. So in that case, again, the product formation will not take place. I can give you an example. For example, we have NO2, two molecules of NO2, they combine to form N2O4. Now, if you look at here, if the orientation of, you can say, NO2 is in this manner, okay, if suppose they combine in this manner, then what will happen? They will form a product. Okay, they will form a product like this. So you get the formation of N2O4. Now, if the orientation of these NO2 molecule is not in line, that is, if n is not near n, then the formation of N2O4 molecule will not take place. So that's a very important underlying factor, that though the collision, the number of collisions which are taking between the reacting species are very high, but it's the energy and orientation factor that always counts towards the formation of products. Okay, so the rate of reaction can be shown as the product of the fraction of effective collision and the collision frequency. So small f is the fraction of effective collision multiplied with the collision frequency. So that gives us the rate of reaction. Okay, so I hope you have understood it, and I just revise what this collision theory is. Collision theory says that in a particular reaction, there are large number of collisions which are taking place between the reacting mixture, but only those collisions are effective which have proper energy and orientations. Okay, and these are called as the effective collision. Okay, so I hope you understood well the concept of collision theory. Now our next topic will be to understand how rates of reaction will be dependent on temperature. Fine. So I hope you understood all the different factors on which collision theory is based, the energy and orientation factors and all. So now we will revise this whole topic through this video. So watch this video so that the concept becomes more understandable and clear to you. Watch the video.
This video is all about collision theory. Let's consider the reaction between H2 and I2. We'll color the H2 molecules red and the I2 purple. Let's watch them as they move. Was there a reaction? No, there was no reaction. Why not? The basic idea, or the basic premise, of the collision theory is that in order to react, molecules must collide. And as you can see, they didn't collide this time. So does that mean they'll react every time they do collide? Okay, let's watch these molecules as they approach each other this time. This time they did collide, but they didn't react. They bounced off each other unchanged. So why didn't they react? Well, it's because they didn't have enough kinetic energy, or energy of motion. In order to collide hard enough to cause a chemical reaction, that, by the way, is called a successful collision. Particles must collide with a certain amount of kinetic energy. The minimum kinetic energy particles must collide with in order to have a successful collision, that is, result in a reaction, is called the activation energy, or EA. Having anything less than this energy, they will not have a successful collision, and there won't be a reaction. Having this energy or greater will give them a successful collision. Let's consider this collision, this time with a little more kinetic energy. When the particles collide with enough energy, they form an unstable combination of atoms. This is called the activated complex, and in this case it has the formula H2I2. If they collide with enough energy, the bonds in the H2 and the I2 will break. And then what happens is new bonds will start forming between the H's and the I's. Now what happens is the new HI molecules, called the products, start moving away from one another. So the chemical reaction is now complete. The two new products, two molecules of HI, have now been formed and are stable. We can summarize this whole process now. The reactants, H2 and I2, collide to form the activated complex, H2I2, an unstable arrangement. The activated complex then breaks up to form the products, two molecules of HI. Okay, watch this collision between H2 and I2 molecules. Was this collision effective? No. Why not? Well, let's take a closer look. Notice how the red H2 molecules are oriented in space, like that. When the molecules collide, the red H2 molecules are not oriented in the correct way to form the activated complex. They're not lined up the right way. Recall that in order to form the activated complex, they should have been oriented this way, so each H can hit an I. In this case, they form the activated complex, and this is called a successful collision. But that's not what happens in this collision. We can say that these molecules do not have the proper orientation for a successful collision. We can also say that they don't have the proper collision geometry. One more term we can use for this is alignment. We can say the molecules don't have the proper alignment for a successful collision. So we can now summarize a collision theory. The three requirements for a successful collision. The first one is the molecules must actually collide. They can't miss. The second one is they must collide with sufficient kinetic energy, greater than or equal to the activation energy. And the third requirement, they must collide with the proper orientation, alignment, or collision geometry. In that case, there's no reaction because they didn't have the proper collision geometry. In this one, there is a reaction because they did.